So lesson 3-1 talks about graphing relationships, and you're looking here at a graph that has three different graphs on it. Graph number 1, graph number 2, and graph number 3, which is very busy. We are comparing speed versus time, and your job is to figure out which graph represents climbing a hill and sledding down that hill. Is it graph number 1, number 2, or number 3? Some things that might help you make your choices would be step 1, read the graphs from left to right to show time passing. So as time increases, what is happening to speed? And step number 2, it might be helpful to list the keywords in order and decide which graph shows them. So where was the graph constant? You would see, where was the graph constant? You would see a horizontal line. Where the graph rises steadily, you would see the graph slanting upward, not real steep, just slanting upward. Where the graph stayed the same, again would look horizontal. If you see the graph dropping sharply, or the rate dropping sharply, then your graph is going to be slanting downward. So what you want to do is think about what happens when you climb a hill and sled. So what you want to do is look at the graph and compare speed to time. So as you're looking at speed versus time, this graph right here, graph number 1, speed starts out high and it gradually decreases to a low speed but not 0. Whereas on graph 2, speed starts at 0, it increases to a maximum, and then it slowly decreases till we get to 0. So speed is increasing and then decreases. Whereas this graph number 3 is kind of interesting. It increases, maintains constant speed, decreases and comes down to 0, and then it increases rapidly to a maximum and then decreases back to 0. So I want you to pause the tape, pause the video, and you figure out whether it's 1, 2, or 3. Okay, now that you've had time to kind of decide which graph is climbing a hill and sledding down the hill, a lot of you are going to have chosen graph number 2, which is incorrect. The reason why you're going to choose graph number 2 is because it looks like you're climbing a hill, getting to the top of the hill, and then you're sledding down the hill to the bottom. This would be the correct graph if we were comparing distance, like a height, to time. You would, as time increases, you would, increase your height and then slowly decrease your height as you sled down the hill. So graph number 2 is actually a picture of the height of the mountain as you climb it and go down the hill. So graph number 2 is incorrect. Most of you will not have chosen graph number 1 because you don't start at a high speed and go down to almost 0 but not quite 0. Graph number 3 is actually the graph for climbing a hill and sledding down, and here's why. As you start to climb the hill, you're at speed 0. You start your climb and you increase your speed until you reach a constant speed as you're climbing that hill. So you keep climbing the hill at that constant speed that you've reached until you reach the top of the hill. So as you're reaching the top of the hill, you're slowing down to do what? You're going to get on your sled. So right here, and so I'm going to write that, right here is where you get on your sled. So all of this right here was climbing the hill and maintaining a constant speed and then slowing down until you stopped to get on your sled. You get on your sled and then all of a sudden from here to here you're zooming down that hill, so your speed is increasing rapidly until you reach a maximum speed, and then the gravity takes over and you slow down until you stop at the bottom of that hill. So graph number 3 is actually the correct graph, not graph number 2. So let's go to the next slide. So you have either continuous graphs or discrete graphs. Excuse me. A continuous graph is a graph made up of connected lines or curves. So each of these points right here are all connected, And then you are comparing temperature versus date. So as the dates increases, or time in this case increases during the week, the temperature is going up, then it drops significantly, drops a little bit more, and slowly climbs back up. So there is a pattern to that temperature, if you will. Versus a discrete graph is a graph made up of unconnected points. And a discrete graph can be otherwise known as, let me get a color here, a scatter plot. Oh, that's way too big. Let me erase that. All right, let's try this instead. So this is otherwise known as a scatter plot. Now, scatter plots oftentimes have various correlations. So you could either have a positive correlation, or it can be a negative correlation. I'm running out of room. And within each of these positive and negative correlations, you could have a strong correlation or a weak correlation. It's also possible that you would have no correlation. So something that would have no correlation or no relationship would be the number of hours that you studied for a test compared to the number of animals you own. Those two have nothing to do with each other. The number of animals you own is not going to increase the number of hours you study for a test, and the number of hours you study for a test is not going to be affected by the number of animals that you own. However, something like the grade you earn on a test is affected by the number of hours that you study for that test. So the more hours you study for a test, theoretically, the higher your grade on that test. And vice versa, the fewer the number of hours you spend on a test, the lower your score should be. Now this particular scatter plot has a definite pattern to it. I could draw what's called a best line of fit going in that direction. So this is called your best line of fit. And that best line of fit kind of approximates the data. You put about half the data above the line, half the data below the line. And it kind of determines the pattern of those scattered dots. So on this particular graph, we have the number of hours of exercise versus the number of months the machine was owned. So when you first get the machine right here, it's brand new, it's exciting, you spend a lot of time on that machine. Versus as time increases, studies have shown, the more you own that elliptical machine or that treadmill, the less time you tend to spend. So there's a negative correlation to that. And I know that this is negative because as my time is increasing, my number of hours that we're using that is decreasing. So remember, a positive and a negative makes a negative. Whereas if they were both going in the same direction, it would be positive. If they're both increasing, that's positive, or if they're both decreasing, that's positive. And a positive correlation would be going in that direction. So this is a discrete graph, also known as a scatter plot, and you can put in that best line of fit. So then let's look at the next slide. On this slide, you're going to sketch a graph for each situation, and you're going to tell whether the graph is continuous or discrete. Sometimes when a graph is discrete, which is that scatter plot, if it's a really strong correlation, it's hard to tell if it's an unconnected graph. In other words, you don't connect the dots, whereas more like a scatter plot, or if you could connect the dots. So example 1 is kind of an example of that. Let's look to see what's going on. Simon is selling candles to raise money for the school dance. For each candle he sells, the school will get $2.50. He has 10 candles that he can sell. So right now, the two things that are being compared, and that's what you have to decide, would be candles. So depending upon how many candles he sells, depends on how much money the school will get. So money the school receives versus candles. So if we were to draw a sketch of the graph, Here's my X and Y axis. You have to decide what goes on this axis here, which should be your independent variable, and what goes on this axis here, which is your dependent variable. Now to determine which is independent versus dependent, think to yourself, which one depends upon the other? Does the amount of money the school gets depend upon how many candles Simon sells, or does the number of candles Simon sells depends upon how much money the school gets? If you think about that, the amount of money the school gets depends on the number of candles. So the candles is what we call our independent variable. So we need to put the number of candles sold on this x-axis, which this is your x-axis. And then on the y-axis here, we're going to put amount of money this school receives. So we're going to partition this graph into 10 pieces, and I'm going to label it every 5 because he only has 10 candles to sell, so I'm going to go out to 10. And I'm going to partition the y-axis up to 10 because for every one of those 10 candles, the school is going to receive money. So for the very first candle, don't mind the barking of the pug. Pizza has arrived at my house, so sorry for the interruption. So for the very first candle that's sold, the school will receive $2.50. So this very first hash mark is $2.50. So this hash mark here is $5. Then every other hash mark will be another 5. So that would be 10, 15, 20, and up here is 25. So if we were to plot, and I'm going to plot in purple, what happens, so if we sell no candles, the school gets no money. If we sell 1 candle, the school will get $2.50. 2 candles, $5, and so forth. See, 5 candles. Whoops. I just put that in the wrong spot. So that's our graph for Simon selling his candles. Now technically, we could connect those dots. There's a definite pattern. It's a positive correlation. As the number of candles sold increases, the amount of money the school receives increases. They're both going in the same direction. That's a positive correlation. This is a scatter plot with a very strong positive correlation. So this is a discrete graph. Whoops. Let me get my pen. So let's look at the second situation. Angelique's heart rate is being monitored while she exercises on a treadmill. While walking, her heart rate remains the same. So while try that again. While walking, her heart rate remains the same. So if she walks, her heart rate doesn't increase, it doesn't decrease, it remains constant. So that's going to look like a horizontal line. Then as she begins to increase her pace, her heart rate rises at a steady pace. So when she increases her pace, her heart rate rises at a steady rate. So it's going to go up. Then when she begins to run, let me change colors. So running, her heart rate is going to increase more rapidly. So it's still going to go up. It's going to go up at a steeper climb. And then it remains high while she runs. So you're going to have another constant right there. It remains high while she runs. So she starts running, her heart rate increases rapidly, and it kind of stays at that constant amount until she stops running. So as she decreases her pace, her heart rate slows down and then returns back to her normal rate. So again, as she decreases her pace, her heart rate slows down, but then it returns to her normal rate, which would be, we're going to go back down to purple. and returns to her normal rate. Or whatever that be. Actually, that's going to be a lower rate than her walking, because walking is going to increase her heart rate. So let me give it one last color. And there's a reason why I'm color coding this. So this is her normal rate. Okay, so let's go ahead and make the graph. And the two things that we're comparing would be her heart rate over time when she's doing all of this walking, running, slowing down, and that kind of thing. So the independent variable, which goes on the x-axis, is time is always independent of anything. Nothing can affect time. So we're going to put time here, and we're going to put heart rate on the y-axis. So her heart rate definitely is not going to be at 0 at time 0, because if her heart rate is at 0, she's going to be dead. So she definitely starts somewhere at some normal resting heart rate. And so she's going to start to walk. And as so let's go ahead and let's just start off with her normal heart rate. So if this is her normal heart rate, she's going to start to walk. And walking, just the act of walking, is going to increase that heart rate, and it's going to go to a steady whatever it is. Okay, and then she's going to increase her pace, and so that's going to raise her heart rate a little bit more. And then she starts to run, and as she runs, her heart rate rises even higher, so that's a steeper climb. And then it remains high while she runs. So she continues to run a little bit, and so her heart rate levels off or remains constant. And then she's going to decrease her pace, so maybe she just slows down to a jog, and so her heart rate's going to go down until she returns back to her normal heart rate, whatever that is. And so you notice that we don't have any numbers here or here because we weren't given any values like we were with Simon's candles. So I don't know what her resting heart rate is. I don't know what her heart rate becomes as she walks or runs. I can only guess that her graph would look something like this. Last slide. So you were to write a possible scenario for this given graph. Water level versus time. Water level increases, then it's constant, and then it decreases. And this would be 0, that would be 0. So I'm going to give you a moment to think about your scenario. So if I were you, I would pause the tape and then restart it again when you come up with your scenario. All right, over time, the majority of students come up with the following scenario for water level, and then there could be various different things that you're filling. So you should be filling something with water. You shut the water off so that it maintains that constant water level, and then you drain whatever it is you're filling. So whether you're filling a swimming pool or a bathtub or whatever it happens to be, you're going to turn on the water. To fill, and let's let it be a bathtub, to fill the bathtub. When the tub is full, you shut off the water, and that's important. The water does not continue to run. So you take your bath, whatever, when you're done with your bath, so after your bath, you pull the plug, get some more room here, you pull the plug and drain the tub. Simple as that. And you're not going to create the graph medley or complete the graph medley. So you're done.